Somebody once told me the world is gonna roll me. I ain't the sharpest tool in the shed.
Since the beginning of your education, you have looked at different numbers and classified them. And we are finally getting to almost every type of number there is. You have a couple more to learn, but this is a pretty inclusive group. And when you are first learning numbers, you learn the natural numbers 1, 2, 3, 4, 5. I think that you get the point. This is kind of where you start out. Then you add a number to the beginning of it, and that is 0. So the natural numbers are not only natural numbers, they are also whole numbers. However, the number 0 is not a natural number. Okay? We add another group to this, and those are integers. And integers are similar to our whole numbers, but they have negatives. So they are essentially the opposite of your natural numbers. So that's why I've got -3, -2, and -1. 0 is an integer. 1, 2, and 3 are integers. Then, and we work with the next group throughout, but we don't really start labeling them until you get to about junior high. And these are all of your other numbers. And these are going to be your rational numbers, and they can be fractions and decimals. So if you have 1/2 or 0.5, that is the same value, and it falls into that rational number category. So while I put they can be fractions, that is implying that the decimal equivalent to that fraction is also in the rational number group. And then here in the 8th grade, we add another group which is not included in the rational number, integer, whole number, or natural number classification. It's kind of off to the side on its own. Okay, so this group is called irrational numbers, and these are numbers that are represented by non-repeating, non-terminating decimals and their opposites. A non-repeating decimal would be, some decimals will be 0.232323. That is a repeating decimal because it keeps going and it creates a pattern. That would be in the rational number category. A non-terminating decimal, well, a terminating decimal is going to be one that stops. Okay, so if someone is terminated from their job, then they stop working there. For instance, 0.25. There's nothing after that 5. There's no additional value there. So that is a terminating decimal. It belongs with rational numbers. So if it is non-repeating, there's no pattern. And if it is non-terminating, meaning it goes on and on forever, then it is an irrational number.
So let's talk a little bit about rational numbers. Rational numbers. And the simple way to think about it is any number that can be represented as the ratio of two integers is a rational number. So, for example, any integer is a rational number. 1 can be represented as 1 over 1, or as -2 over -2, or as 10,000 over 10,000. In all of these cases, these are all different representations of the number 1, ratio of two integers. And I actually obviously can have an infinite number of representations of 1 in this way, the same number over the same number. The number -7 could be represented as -7 over 1, or 7 over -1, or -14 over +2, and I could go on and on and on and on. So -7 is definitely a rational number. It can be represented as the ratio of two integers. But what about things that are not integers? For example, let us imagine, let's imagine 3 3.75. How can we represent that as the ratio of two integers? Well, 3.75, you could rewrite that as 375 over 100, which is the same thing as 750 over 200. Or you could say, hey, 3.75 is the same thing as 3 3/4, So let me write here, 3 3/4, which is the same thing as, well, that's 15 over 4. 4 times 3 is 12, plus 3 is 15. So you could write this. This is the same thing as 15 over 4. Or we could write this as negative 30 over negative 8. I just multiplied the numerator and the denominator here by negative 2. But just to be clear, this is clearly rational. I'm giving you multiple examples of how this can be represented as the ratio of two integers. Now, what about repeating decimals? Well, let's take maybe the most famous of the repeating decimals. Let's say you have 0.333, just keeps going on and on forever, which we can denote by putting that little bar on top of the 3. This is 0.3 repeating. And we've seen, and later we'll show that how you can convert any repeating decimal into a rational as the ratio of two integers. This is clearly 1 over 3, or maybe you've seen things like 0.6 repeating, which is 2 over 3. And there's many, many, many other examples of this. And we'll see any repeating decimal, not just one digit repeating, as many, even if it has a million digits repeating, as long as the pattern starts to repeat itself over and over and over again, you can always represent that as the ratio of two integers. So I know what you're probably thinking. Hey, Sal, you've just included a lot. You've included all of the integers. You've included all of non-repeating decimals, or you've included all of finite non-repeating decimals, and you've also included repeating decimals. What is left? Are there any numbers that are not rational? And you're probably guessing that there are. Otherwise, people wouldn't have taken the trouble of trying to label these as rational. And it turns out, as you can imagine, that actually some of the most famous numbers in all of mathematics are not rational. And we call these numbers irrational. Irrational numbers. And I've listed just a few of the most noteworthy examples. Pi, the ratio of the circumference to the diameter of a circle, is an irrational number. It never terminates. It goes on and forever, and it never repeats. E, same thing, never terminates, never repeats. It comes out of continuously compounding interest. It comes out of complex analysis. E shows up all over the place. Square root of 2, irrational number. Phi, the golden ratio, irrational number. So these things that really just pop out of nature, many of these numbers are irrational. Now you might say, okay, are these irrational? These are just kind of these special kind of numbers. But maybe most numbers are rational, and Sal's just picked out some special cases here. But the important thing to realize is they do seem exotic, and they are exotic in certain ways, but they aren't uncommon. It actually turns out that there is always an irrational number between any two rational numbers. And in that, well, we could go on and on. There's actually an infinite number. But there's at least one. So that gives you an idea that you can't really say that there are fewer irrational numbers than rational numbers. In a future video, we'll prove that you give me two rational numbers, rational 1, rational 2, there's going to be at least one irrational number between those, which is a kind of a neat result because irrational numbers seem to be kind of exotic. Another way to think about it, I took square root of 2, but you take the square root of any non-perfect square, you're going to end up with an irrational number. You take the sum of an irrational and a rational number, and we'll see this later on. We'll prove it to ourselves. The sum of an irrational and a rational is going to be irrational. The product of an irrational and a rational is going to be irrational. So there's a lot of irrational numbers out there.
Only shooting stars break the